We talked a little bit about organic chemistry on Friday there. Remember, organic chemistry is the study of carbon-based molecular compounds. Nearly all carbon-containing compounds are classified as organic. Here's a few exceptions, of course. We would call these inorganic. So like things like carbonates, cyanides, carbides, and carbon dioxide. So carbon oxides, basically, okay, are not organic. The diversity of organic compounds is based on several factors, of course, we talked about. Carbon has the ability to form 4 bonds around itself, so it leads to lots of different types of structures, which we're going to start talking about today. We could talk about single bonds, double bonds, triple bonds between carbons, and carbon atoms can bond together in chains, and we're going to start talking about that today with different lengths. These factors allow carbon-based compounds to exist as isomers. Don't forget, isomers are the same formula, but a different structure. And we're going to get you to draw a few of these today here. C4H10, both of these are C4H10. By the way, listen closely. These are both isomers of C4H10. So it's not that this is the main one and this is the isomer. These are both called isomers. Isomers are compounds with the same formula but different structure. So these are 2 isomers, okay? C4H10 can look like that, or C4H10 could look like that. They have different names, they have different properties, and we're going to look at that today here, okay? Don't forget, this one here is linear kind of ish. This one was spherical, if you remember. So difference between the boiling points there. This one's probably going to have a higher melting boiling point because it's linear. It has a better shape to stack on top of the other one, more surface area for contact. This one is spherical. So when you think about how much does this one affect this one, not as much, okay? Less surface area to contact there, less London forces there, okay? And you can see that with the boiling points here. One is 0.5 there for the spherical, or sorry, for the linear one is negative 0.5, about 0-ish, say, and this one here is a negative 12, it's weaker, okay? Butane cylindrical shape has stronger London forces than the spherical shape, and then we get to drawing organic compounds here. I think this is kind of roughly where we left off last day, isn't it? Okay, so there's different ways of representing these types of molecules. The first one, of course, is empirical molecular formula. This is fine. If they said, you know, draw some isomers of C5H12, that would be okay. But this doesn't tell you what kind of shape this is. All it tells you how many carbons and hydrogens there are, and it could be multitudes of shapes. In some cases, we'll see. We're going to draw some isomers today, and you'll see how many different options you have for some of these formulas. So it makes no attempt to specify what it actually looks like. It just says, hey, here's 5 carbons, here's 12 hydrogens, you make your own diagram kind of thing. Okay, C5H12. Expanded molecular form does show groupings of atoms, and bonds are assumed to exist between atoms, of course. So we have to assume that there is bonds here. We don't show them, of course, but you know that there's CH3 linked to CH2 to CH2 to CH2 to CH3. And I think I did this last day for you as well. Obviously, guys, if you had carbon can have 4 things around it, you wouldn't do this, correct? That can't happen, right? Because hydrogen can only form 1 bond, yes? Because it's only got 1 valence electron. So that's not an option for you. So when they draw this here, they're obviously telling you it's, you know, in this case here, it's C to C to C to C to C kind of thing, and then the rest is filled in with H's kind of thing. And that's actually going to be like something that we look at the next structure. So that's called the expanded molecular form. Expanded molecular form. Complete structural diagram. Okay. Sometimes this is nice to give us an exact, clear picture of what this is going to look like. Okay, so there's no doubt about it. This is what the formula, this is what C5H12 can look like. This is the one we are talking about. There's no doubt about it. Shows every bond, shows every atom linked to everything, complete. Okay, there is also a condensed structural diagram, which is the one we probably use the most. Okay, condensed structural diagram shows, basically to save some space, just shows the carbon to carbon bonds here. So the carbon to carbon bond, carbon to carbon, carbon to carbon, carbon to carbon. And then we just put in the appropriate number of hydrogens that we need to fill in those carbons. So remember, there's 4 things around every carbon. So we need to make sure we have 4 things around every carbon. So C to C, that's 1 bond there. Okay, so that's your 1 bond there. And then you'd have your 3 H's coming off of there. And that's where we put that right there instead. Okay, so that's called the condensed structural diagram. Okay, and then finally, last one here is what we call a line structural diagram. And the lines represent chemical bonds, and at the end of each line represents a carbon atom unless you otherwise specify. Okay, and we're a long ways away from that probably. Each carbon is assumed to have as many hydrogen atoms bonded to it as, you know, the 4 hydrogen or the 4 bonds around carbon. So basically what they're saying here is at the end of every line there's a carbon there, there's a carbon there, there's a carbon there, there's a carbon there, there's a carbon there. Don't forget the ones at the end, because that can really mess you up, obviously. If you miss a carbon or miss a hydrogen even for that matter, guess what? Molecular mass is off, right? Molar mass is off. And where do we use these questions? What are hydrocarbons very good at? Burning. Burn, 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 right? Yeah, right? We use them as fuels all the time. So where do you think we're going to use these mostly? Probably in combination with unit 1, I would think, eh? Because if we're combusting something, we can figure out the enthalpy, yeah? And if we can figure out the enthalpy, we could find out the molar enthalpy. We could figure out, oh, geez, lots of stuff, yeah? How many grams of pentane do I have to burn in order to get an enthalpy change of 1,000 kilojoules per mole, kind of thing, all right? So, lots of potential for these types of questions with burning, all right? So there is 5 carbons here, and of course you have to assume that the rest is filled in with hydrogens. You just assume so. Now, having said that, you might say, well, why didn't we just draw a straight line? Well, if you draw a straight line, how many carbons do you have on there? Well, technically 2, right? That's it. You'd have 1 here and 1 here. So the reason they do this is to show you all the different carbons, of course, that there's 5. And the second reason they do this is because this is actually what carbon-to-carbon bonds look like. If you actually look at a carbon-to-carbon bond here, here's carbon here, okay? You know, if you want to talk about carbon-to-carbons here, stupid. All right, here we go. Okay, they kind of make this, I mean, we call it linear, and we like that because, you know, I'm actually gonna cheat here. I'm just gonna do 4 in a row. There's, let's see here. Let me get these organized properly. There's 4 in a row for you there. That's not pentane, of course. That's not 5, but that's 4. You can see they make that zigzaggy pattern, right? Because that's kind of how they're associated. Remember, those bond angles aren't 90 degrees apart because it's 3-dimensional, right? So you got to kind of keep that in mind. So you might say, is it linear? It's still linear this way. It's a little bit, it is linear-ish, yes, this way. It's just that it has to go up and down because that's the way it goes. So that's actually what it looks like, right? Maybe I should have put this one. Oh, whatever. That's fine. Okay, anyway. So it does that kind of zigzaggy thing anyway. So that's why, okay? You can eventually, listen, you can make double and triple bonds on these as well. To make a double bond, you would probably put in this line here, of course. So I put that one in there, and I'd put another one like that. So that would be a double bond. If you want to do a triple bond, I'd put another one on there, for example, like that. That would be a triple bond, okay? So you can still do double and triple and single bonds. We're a little ways away from double and triple yet, but we'll get there eventually. Alrighty? Good? Good. Perfect. All right, so there's 2 other isomers of C5H12. Write out condensed structural diagram for these 2 isomers, so let's do that now. All right. Well, I'm going to start with the most common one, and they're saying there's 2 other isomers besides the one that they gave us, C5H12, the example. So they're saying, hey, here's C5H12. What is that, 5? Okay. This is the one we did all the examples with, C5H12, and that's called pentane. Okay, and we're going to talk about how you name that today. All right. They're saying there's 2 other isomers besides this one. Okay. Now this is a little bit tough for you guys because it's the first day, And once you actually do the second lesson, which is naming, then it becomes a little bit easier. But I'll kind of introduce a few concepts to you as we go through this, and that'll become more clear when we do the actual lesson 2 here, which we're going to probably get into a little bit today here. Okay? So this is pentane. This is an isomer. Remember, all of them are going to be isomers, but there's 2 other ones besides this isomer as well, they're saying. 5 carbons in a row. Is there any other way that I can put these together with 5 carbons in a row? And the answer is not really. Okay? After 5 carbons in a row, how am I going to arrange them differently so that I get 5 carbons in a row, but it doesn't look like the first one, for example? And the answer is it's going to be pretty tough. Okay? So we're going to drop down to 4 carbons in a row. And so I got 4 carbons in a row. My question now is, one of the things we're going to talk about here is these chains of carbons. And you always kind of want to look for long chains of carbons. So here's 4 in a row. Now listen, if I put a I said, that would be the same as that one, yes? If I did that, you agree? What if I do this? Is that the same as that one there? The answer is yes, it is. Because technically I still have 5 carbons all lined up in a row. It would be like kind of taking these 4 here, and then, ultimately, here, I'll show you. How am I going to switch that? If I have 4 in a row, okay, there's 4 in a row, how am I going to stick this one on to make it different on the end? And the answer is, well, if I stick it here, right, well, that kind of looks like, to me, 5 in a row now, right? Okay, well, you might say, okay, well, I'm going to stick it on to this one here, but that's the same thing. You see what I'm saying? And I'll stick it on to the other hole here. Well, it's going to be the same thing. I'm going to ultimately get 5 carbons in a row here, and you can adjust it however you kind of want to, but basically you're going to get this same shape over and over again. Okay? I mean, you might say, well, that's, or that's a little different, but I'd argue that's still 5 carbons in a row. Okay? And so that's not going to work out for us, so I'm going to get rid of that. Now what I would probably do is say, okay, well, if I put it on this end, that's 5 carbons in a row. If I put it on this end, same thing, right? I mean, kind of the same thing. So let's not put them on the ends. I would say let's stay away from that, because if I did, I'm going to get 5 carbons in a row. Let's put it in, let's put it right here, for example. Is that one different than that one there? Yeah, that one's different. Okay, so that's another isomer that we can talk about for C5H12. We'll fill in the rest with H's here. Okay, and you might say, we got, once again here, okay, and I put in the H's there because, of course, I know that H carbon needs 4 things around it. So I said, well, here's 1 thing around the carbon. I put another 3 in there for 4. I had 1, 2, 3 things around this carbon already, so I only need 1 hydrogen there, 4. I had 2 here, so I put 1, 2. And I had 1 there, so I put 3. And then down here, I had 1, so I put 3, yeah? So 4 things around the carbons, yeah? So there's another one. Okay, so let me say, let's see here. If you want, I can show you this one here. I'll take it off of this one. Here's 4 carbons in a row, and I'm going to stick that one there. Okay, there you go. That's basically that one. Well, actually, that's that one there, technically, yeah? Okay, so that's kind of what that one looks like there, roughly. Okay, good. I got 4 carbons. Let's try and make another 4 carbon one in a row here. Okay, because it says there's 2 other isomers, so there's got to be another one. Well, there's 4 carbons in a row, and I'd say, okay, well, I put it on this one here, and remember, I want to stay away from the ends, because the ends gives me 5, so I don't want that. What if I put it here instead? Is that different than the one above it? And I would argue probably not, because what I would do then is I'd say, okay, well, there's that one. Is that different? Did I make something completely new by doing this? No. Okay, molecules are allowed to turn over and flip over and stuff like that, right? So that one and this one are not, well, did I do anything to this to make it different? I turned it, no. Okay, so that's not different. So, okay, well, that doesn't work. Well, I've kind of used up all my 4 options then, haven't I? Because what else am I going to do here? I can't, I said I can't, you know, I put this one here, I moved it over to here. I can't put it on the ends because that gives me back to 5. That's actually the top one there. So now what am I going to do? Well, I'd say probably I'm done with the 4 option, right? 4 carbons in a row. What if let's try 3 maybe. Can I do something with 3? And now we're looking at something like this here, right? Let's take this one off and this one off. So here's my 3 option. Can I do anything with this? You know, and I'd say, well, let's put a carbon on to start with. Do I put it here? Well, that's 4 in a row again, isn't it? So I don't want to do that. Can I put it here? No, because that's 4 in a row again, right? That would be this one, is it not? So what if I put 1 here? What if I put 1 here? Is that different? Can I do that? How many do I have in a row there? The answer is 3 in any one particular direction, right? Basically what I'm asking you is this different than anything else I've done so far? You know, looks different to me, right? So I would say that's another option here. And once again, you need to go back and fill in some H's here. So let's see, H, H3, H3, right? 4 things around each carbon. The middle carbon does have 4 things around. It's actually, and by the way, what shape is this again? You guys remember from Chem 20? 4. Tetrahedral, yeah. Bond angle is 109.5, yeah. Things like that. Okay? So, there is your other 2 isomers. And one thing I have to mention here, obviously, there's 3 drawings of C5H12. They all have different properties. I would probably assume, you know, if I was looking at this and if I didn't look it up in a book or anything, I'd probably assume this is the best melting boiling points because this would have the strongest London forces because it's linear and another linear one together. And I would assume that this one's probably the worst, yeah? Because it's spherical. Well, look, you can see spherical, right? And to another spherical one, probably low London forces in that case. Nonetheless, what I'm saying to you guys is these are all isomers of C5H12, okay? Those are all considered isomers because they all have C5H12 as a formula. It's not that here's this one and these 2 are isomers. That's not the case. These are 3 isomers, okay? So, you know, just kind of remember that, please. Like when they talk about isomers, we're not talking about one. They're all isomers. That's what I'm trying to say. Okay? Good? Yeah? All right, let's take a look here. There's 5 isomers of C6H14. C6H14. Is that the last one we have? Oh, it is. So I'm going to let you guys go ahead and do, let's get as many as you guys can get. C6H14. Apparently there's 5 different diagrams. I know which one I'd do first if I were you. But that's just me. I'll let you guys keep going here. I'll just do a couple of these obvious ones maybe first. Hopefully obvious, I don't know. There's 6 in a row, so that's pretty straightforward, obviously. Let's see here. Let's do, once you get 6 in a row, by the way, 1, 2, 3, 4, 5. Guys, once you do 6 in a row, you're done. Okay, with 6, you're not going to do anything else with 6. There's nothing else. You get 5 in a row. Once again, I'd want to stay away from the ends because if I put one on the end, it's just going to be 6 in a row again. I don't want that. So I'd say, oh, let's throw one in here maybe. Okay, that's different. That's 5 in a row. And you got that 1 carbon coming off of there. And in fact, while I'm at it, I'm just going to draw, let's see, is there any other ones I can do with 5 in a row? Is that one, let's move this over one. Can I do that? Is that different than the top one? The next, or the one right above it? Is that different? If I flip the top one around, or if I flip it over, or can I match those 2 up, is basically the question. Are those 2 going to match up? The answer is no, those are different, okay? There's nothing I can do. This one is kind of off the 2nd carbon here. I can turn this around if I want, but that's not going to equal that one there, okay? So that is in fact different. Those 2 are different. I'm going to come back to, just give me 1 second here. What is that, 5 in a row again? Is this one different than the other 2 here? No, that one is the same, yes? These 2 are the same, correct? Take this, take the bottom one and flip it around. Do you not agree? Those are the same, yes? Okay, so that's not an option for you. That's the same. So let's get rid of this one here. Okay? But those two are different. Those two don't look the same. You might say, well, what if I did this? Can I do, what if I put the C on top? Is that different than the top, than this one here that I drew a line to? No, take this one and flip it around, right? Flip it over. Is that right? Those two are the same, yes? Again, so we don't want that one either, right? I would say probably at this point, guys, you're probably done with the 5 in a row ones, because where else am I going to put that other C to make 5 in a row that's not the same as something else? So I'd say we're probably done in this case with 5 in a row. So let me get rid of, let me put some H's in here. That would have 3 around it. There's 1, 2, 3 things there. I need 1 there, need 3 there. I need a 2 there. I need 2 here, and 3 there. Okay, and over here I need 3. 2 things around that one. I need 1 there. I need 3 down there. 2 there, and a 3 here. Okay? And obviously, you know, if you want to double check them, they have to add up to C6H14, of course. All right? So that's 3 isomers so far we got. That's okay. We got to do another 2 yet. We've done 5 in a row. We've pretty much exhausted that, I think. Let's do 4 in a row. Okay? So there's 4 in a row. Now I got to put 2 carbons on here somewhere. Well, once again, I want to stay away from the ends, because if I put a carbon on the end here, guess what? I have 5 in a row, and I just finished telling you that we've done all the 5 in a row ones. So I don't want to do that. You got to put them in the middle somewhere here, so maybe I'll put 1 here. Where do you want to put the other one? On top? Sure. Is that one different than the other ones there so far? Yeah? That's different. 4 carbons in a row, and there's 2 on the same one there. That's different. I don't have 2 on any other carbons here. Okay, so that's a little different. Only 4 in a row there. Yeah. So that's an option. Okay. Let's fill in the rest here. H3. That carbon's good. It's got 4. That's a 3 there. That's a 3 there. That's a 2 there, and that's a 3 there. Okay. Good. Let's see. Is there any other 4 ones I can do? Any other 4 ones? I can't put them on the ends, because once again, even if I put 1 on the end, that's going back to 5 carbons in a row, yeah? So I don't want that. Can I put 1 carbon here, let's say, and can I put the other one here? Is that different? Sure, that's different. Okay, that's a little bit different. We haven't done anything like that. If you take any of those other ones and flip them around and flip them over, do you get that diagram there is the question. And the answer is no. Okay, so this is the other one. And I think we're done, actually. That one does need an H there. That one needs an H. That's a 3, and that's a 3 there. Okay? So those are your 5 isomers of C6H14. Somebody might say, well, what if, can we do, let's go a little bit farther. Can we do 3 in a row? Is that an option for us? And the answer is, well, 3 in a row. So what are you going to do? Well, where are you going to put these? Well, obviously, if I put 1 on the end here, I'm going to get 4 in a row again, right? Correct? I don't have and I don't really have a choice, right? Because if I put 2 C's here, that's fine. That's great. But where's the other one going to go? Well, it's either going to go on this one here or this one here. You might say, what if I put it on here? Well, then you got to start turning stuff, right? You know, I'll put a C over here, for example. Well, that's, look, 1, 2, 3, 4 C's in a row. Do I have 2 C's coming off that 4 one, like one above each other? That looks pretty much like that, doesn't it? Is that not the same? That's not an option. Okay. Then somebody's going to say, okay, well, what about, hey, Bachek, put 1 off of here somewhere. Put 1 there. Okay, well, there's 4 C's, and I got 2 coming off this one here. Let's turn this like that a little bit, right? In fact, I could probably do that if I had the power. No, I can't, but that's okay. Well, I could, but I'm not going to. That's going to take too much time. But I could take that one, right? Look, I got 1, 2, 3, 4 C's, and I got 2 coming off that second one there kind of thing. Look, 1, 2, 3, 4 C's and 2 coming off. Isn't that the same thing, just turned? Sure, it is. So it looks like I've kind of done here, yeah? And I've already found, I told you there's 5, and that's all there is. And that's the reason, because it doesn't really matter how you're going to do that. It's going to work out to be the same. Yep. Yep. Please, when we go to name these, please don't call it the sword-looking one. Okay, I'll laugh at you. Just a little bit. Well, if I move this one over to here, no, because these two here, basically these atoms turn and things like that. So yeah, I know what you're saying. One down here and one up here is going to be the same. It will be. And even if you don't think so, remember it kind of does that zigzaggy pattern. You can go 1, 2, 3, 4 in a row, and then you'd have these two as the add-on stuff. So it's kind of complicated to explain that, I guess, right now without the naming part. But yeah, it doesn't matter because they do turn. Okay. Unfortunately, I took it apart. But if you had 4 in a row, I could take those 2 middle ones. I still could, and I could turn them to make those different diagrams. I could. Okay. So I could make this one, or I could make that one up there just by turning this atom here. I could do that. Okay. Yeah. All right. Once again, it's a little bit complicated right now, but if you understand that, that's great. That's fine. Once you get to the naming, you'll see, do you get a different name? That's a different structure, obviously. And I'll show you how to name them properly. And once that happens, then you'll understand which ones are actually different and which ones are the same. Okay? Good. I think that's it for that one, yeah? Good? Okay. Let's